difference?
Oh, well, I wasn't looking that fast, and it doesn't look, it's almost ripe.
It is ripe.
Okay,
Yeah.
you gonna fry it in some butter? Or coconut oil?
No, I use olive oil because I'm healthy.
Okay, I mean, whatever.
Yeah. Yes. This is my knife. I'm not doing anything illegal. I'm just making breakfast.
Okay, well, count all your fingers and toes when you're done.
Yes, I will.
Hi, Miss Baskin.
Hi, Shayla. All right, so based on who I see right now, we are missing William, Lauren, Ioannabelle. Poor Asha, she keeps getting kicked out. Micaiah, but I know about her. Alina, Andy, Eliora, Dalia, Josh, Jayla, and Jada. So we'll see if they end up popping
Which
in.
Jada?
What? Jada Spriggs, sorry.
Okay.
Yes. Other Jada is like, I'm here. And Jameer, am I crazy or did you never send me an email?
Lauren's on the way.
I think well, let me see. I'm pretty sure I did.
Well,
I'm almost like 100% sure I did.
Then you're not sending it to an address that I actually own.
All right, let me see.
Those are your two options for emails. There's Lauren.
Wait, what's your email?
I just put it in the chat.
All right.
You send them my way. Tired of stuff coming.
Hi, Sophia.
Hello.
Hi. These are very nice pillows. Or chairs.
They're chairs. Yeah.
Chairs.
Yeah, I sent it to the wrong email.
Okay. Well, then go send whatever you need to send to the correct email. Just forward it.
Okay.
Okay. And there's Andy and Alina. Okay. Okay, so we'll go ahead and get started. So as I said, today is primarily we're going to be focusing on the calculations. And then I want to go over our change for Thursday because I didn't know we weren't supposed to have school, so that's fine. And then So today is the only day we're meeting. And then we'll go over next week.
How we don't have school if we're not going? I'm confused.
Right. Because it's Thursday is DC's Emancipation Day, when the slaves of DC were freed, emancipated. So it is a recognized holiday in DC. You probably don't realize it's a holiday because it's always during our spring break. So we don't ever separate it or celebrate it separately because it's wrapped into our spring break week. But clearly this year, since spring break got moved, it is still supposed to be observed. So nobody's supposed to work on Thursday. So I'm gonna try not to work on Thursday, but I will probably still send like missing work emails or something like that. But yeah, so we don't have class on Thursday. So I had to make some adjustments because I didn't find that out until Sunday night. So yay, that was helpful. Communication, it's something. All right. So we spent last week going over electron behavior. So I'm going to attempt to use the annotation finger or the annotation feature in my finger on my trackpad to fill in these blanks with you guys. But if it's really bad, we will at least say the words out loud. But we went through how electrons move and generate light. So first off, electrons stay in the blank state. Where are they normally?
Ground.
Ground state.
Ground state. Okay, so look at that. G.
Is this in a packet we have or something?
Nope.
Okay.
This is what happens when Baskin gets bored and makes stuff up. All right. So we are in the ground state unless they do what with energy?
Transfer. Get excited.
They get excited, and how do they get excited? Do they need it or do they give it up?
They give it up.
Absorb.
When they get it, they give it.
Yep. So they're going to get the energy. So they are going to absorb energy.
Miss Baskin,
Yes,
it's pretty hard to see against the background.
Okay, let me see if I can switch colors. Yellow, that'll be annoying. Okay, so electrons stay in the ground state unless they absorb energy. So if they absorb energy, this makes them move which direction?
Up.
To the
Up.
excited state.
There we go. When they move up, they're up now in what state?
Excited.
Excited. If we ever get to go back to my classroom, I will show you the bumper sticker that I have in my car, or not in my car, on my yellow cart that says I'm in an excited state.
Real cute.
It's an electron joke. It's not a good one, but very few nerd jokes are. So, okay. This is what? When you're in the excited state, what do we call that?
Unstable.
They do not like it. Same I am. Unstable. Where did my thing go? This is unstable. Okay, so it's unstable, so that means they're gonna move what?
Back down to the ground and back up.
Yep, back down to the ground state. This is taking me just long enough to do that if you actually wanted to write this out on your own, you could. So when this happens, they will, what? What's the opposite of absorb?
Give.
All right, so give off, which we're gonna say is release. Release energy. And how does that energy come?
With the wavelength? I don't really know.
No, so that energy is as what? How
Light?
does it appear to us?
Light?
Light. And light comes in tiny little packets. And I don't think I actually used this word, but it was in the reading and such. What is a tiny packet of light called?
Photon.
Photon. It is not a proton. It is a photon. It's in photo. And every single photon has a specific wavelength and energy. It's like taking way too much energy. Wavelength and energy. So that's the calculations we're gonna do today, is calculate wavelengths and energy of photons. And that, so the wavelength and that energy is determined by how much the electron moved, and it is unique for every single element. So part of the reason I wanted to go over this little paragraph is because I think that's how you spell unique. Sure. I don't do English. It's because this is basically the whole entire gist of what is going on in the flame test lab. And I'm gonna end up asking you to write something similar to that in that lab. So there you go. If you forget it, you can rewatch the video and you'll have access to it and it'll be here and all that stuff. So, whew, okay, annotation's off. Okay, so that's basically what electrons are doing. They stay in the ground state, they take energy, they go up. Being up is unstable in the excited state, so they fall down. When they fall back down, they cannot hold on to the energy, they have to give it up. They give it off as photons of light, and those photons of light are very specific and unique to the element, and their wavelength and their energy is very distinctive, and that's how we can identify what they are in emission spectrum. So that's that. Oh, I didn't know that state. That's annoying. Cleared all. Yay. Okay. So we are going to move on to this sheet, the calculation practice sheet. You will need a calculator because we're doing stuff. It should be somewhere behind your 5.2 section. And I have to switch over to the iPad. So it looks like that. So see if you can find that. If you can't find that, just grab a piece of paper. It'll be all right. Because again, the video exists. Okay. So these, let's see here. If I remember correctly, this formula is explicitly at the beginning of 5.2. And this formula is mentioned in a paragraph at the end of 5.2. And this formula over here is in 5.3. So these are in 5.2, and that last one is in 5.3. So the first thing I want to point out is we need to make sure we've defined all these variables and we know what the hell the letters are. So the only one of these that actually makes any sort of common sense is the capital E. And capital E stands for what?
Energy.
Energy, the only one that makes sense. Okay. And energy, again, is in joules or kilojoules. So that's how that's going to be given off. none of the rest of these variables or letters look like anything that they actually represent. So the other things in that formula, that H is called Planck's constant. And it's right here. And it's nice that several of these formulas have constants in them because it means there's less numbers in the problem. Like you have it. It never changes. It's always there. And then if I look at this other thing, that is not a V. It is the Greek letter nu. So it's kind of like if you had a V standing in a strong wind and it was kind of blowing like a sail. So it's nu. And that is frequency. And frequency is measured in hertz, which are also known as inverse seconds. So those are all the same thing. You'll remember that frequency is in hertz if you've ever spent any time looking at a radio dial, not dial, that's quaint. The radio frequencies in your car, when you're trying to tune to a radio station, the numbers that are your actual radio station call sign, that is its actual frequency. So they are identified by their frequency. The difference between AM and FM radio is the frequency range of those radio signals. So that's frequency. So that's this equation. So in this other equation, we have nu down there, but there's two other things. So C is another constant, and that is the speed of light. And the speed of light is also a constant, and it's down here. That means every single form of light travels at the exact same speed. So radio waves are a form of light, and they travel at the same speed as the visible light that hits your eyeballs and allows you to see things. Those are traveling at the same speed all the time, and it's 2.998 times 10 to the 8th meters per second. That's really fast, and we think that that is the fastest thing possible, although Einstein would probably quibble with that, but that is not my area of expertise. And then this last thing is a lambda. So that's the lowercase Greek letter lambda, and it stands for wavelength. And our wavelength also is in meters. So what I've done on these other formulas here is I did the algebra already. And I rearranged this formula to solve for the various different variables. So this is the formula if you're looking for the speed of light. This is the formula if you are looking for frequency. And this is the formula if you are looking for wavelength. So based on what the question is asking for, you can just use the right formula. And on the other side, this formula here is a combination of this one and this one. It has combined those two. Because honestly, in chemistry, we don't really care about frequency. We care about energy and we care about wavelengths. So this formula here has energy and wavelength. H and C are constants. So it's actually really, really easy to deal with. And we can even rearrange this. And if I wanted the wavelength and I had the energy, that's it. So those equations, and if I remember correctly off the top of my head, these two equations are going to be the ones you'll end up using on the lab. Okay. I'm not going to focus on this guy as much over here, but I will say that this M is mass in kilograms, and that V is velocity or speed also in meters per second. Okay, so let's actually start looking through these things. So number one, it says list all electromagnetic radiations from low energy to high energy. So that means over here on the left is going to be low, and this is going to be high. So electromagnetic radiation is another way of saying light energy. Anybody know off the top of your head, what is the lowest energy form of light? It's not something you think of as light.
Are they radio waves?
Red?
It is radio.
Oh.
Radio waves. Radio waves technically are a form of light. They can carry information and all sorts of things. They are very, very long waves, which makes them very, very low in energy, which is a good thing because our lives are filled with radio waves. And if radio waves were actually high energy enough to be damaging, we would be dead. Because everything, like there's AM radio, there's FM radio, there's satellite radio waves, there's your 5G, your 4G, your all of those things, that's all radio waves. So like this is our primary form of communication is done through radio waves. Slightly more energy than radio waves is microwaves. Microwaves are an actual thing. Microwave ovens use microwaves. We just kind of leave the term oven off of the phrase, but microwaves are shorter than radio waves. They still do not have very much energy, and the very distinct frequency and wavelength of microwaves that we use in a microwave oven are the exact frequency and wavelength that you need to make water molecules vibrate. And that's how a microwave oven works. It makes the water molecules in your food vibrate, and as they vibrate faster, they generate heat, and that heats up the food. That's why you can't heat up dry things in a microwave, because there's no water to vibrate.
And it makes
there you go. And there is literally nothing to do with any form of cancer or danger with a microwave. That's an old wives' tale. Okay, so radio waves, microwaves. The next thing we refer to as IR, infrared. It's your remote controls. So you can shine a little remote control in your face all day long and it does not do anything to you because it's infrared. It does not have very much energy. But this next chunk here is what we refer to as the visible spectrum. So what is my lowest energy form of visible light?
Red.
Red, because it's right next to infrared, right? Red, orange, yellow, green, blue, violet. Okay, so once we go through the visible spectrum, what's just beyond violet?
Ultraviolet.
Woohoo! UV. Now, we just start with ultraviolet getting into a spectrum of light energy that has enough energy to actually start doing some damage to humans. Not all ultraviolet, but the highest energy spectrum of the ultraviolet range, for those of us who are melanin deficient, we can have problems in the top layer of our dermis, and we can start developing what we think of as melanomas and skin cancer. So the ultraviolet, that higher energy levels of ultraviolet is actually enough energy to pierce the top layer of your skin and damage those cells. So there we go. Beyond ultraviolet, X-rays. X-rays have enough energy to actually go through all of your soft tissue. It makes them useful for medical purposes, but it also makes them scary, and it's why we wear lead blankies over our internal organs when they're not trying to look at our internal organs. And then lastly, the highest energy form of light are gamma rays. And those can just go through everything. So it's gamma rays in addition to some visible light that is coming actually from the sun. Okay, so that is kind of handy to know what's going on. But now let's actually practice a couple of these basic calculations. So this first question, an FM radio station has a frequency of 88.9 megahertz. All right, megahertz. AM is kilohertz, if I remember correctly. And it says 1 megahertz is times 10 to the 6 hertz. What is the wavelength of this radiation in meters? So which variable am I looking for?
Lambda.
I am looking for lambda. Okay, so my equation with lambda, then I have two different options, or actually three different options. Which equation am I going to use?
Lambda equals Planck's constant. No.
It's C over U, right? Or
Yep.
is it?
Yep,
Yes.
it's the C over the frequency, correct. Okay, so equals C over nu, right, the frequency. So that means this thing here, they tell me that's the frequency. So that's this, but I have to use it in just hertz. So here's how I can write that. It's 88.9 megahertz, but they tell me that mega is times 10 to the 6. So here's where I'm going to not care about the actual way that my scientific notation is written. I'm going to say that's 88.9 times 10 to the 6 hertz, because I can enter that in my calculator. Would I accept that as a correct form of written scientific notation? No, I would not, but that's easy to do. So just do it that way. And C is a constant.
Question.
Yes.
Are hertz and the inverse seconds the same thing?
Yep.
Okay, thank you.
Physics people like Hertz because Hertz was a physicist. Physics people like naming units after people. Volts, coulombs, jerks. Okay, so C is 2.998 times 10 to the 8th meters per second. I'm gonna divide that by my frequency, 88.9 times 10 to the 6th inverse seconds. And I'm just dividing those two numbers. This is literally it, dividing those two numbers. So in your calculator, and not everybody may have a scientific notation calculator. If I remember correctly, I know of a couple of websites that you can use if you need one that I'll send out later. But 2.998 EE to the 8th divided by 88.9 EE to the 6th. And how many sig figs should this have?
3.
3. So to 3 sig figs, this would give you 3.37 meters. Because these seconds and inverse seconds end up canceling out.
Miss Baskin,
Yes, it's sure.
when I did in the calculator, I got 0.0337.
Then that has to do something with the way that you entered in the scientific notation.
Okay.
Okay, so if you drive around at all in a car while you're listening to the radio, you know, sometimes the radio station fuzzes out. And if you like inch forward, inch forward, inch forward, you can pick it back up again. That's because radio waves are about 3 meters long, which means that's about 10 feet. So about every 10 feet, your radio station is going to go in and out and in and out. So that's kind of why that happens. Okay, next question. The U.S. Navy has a system for communicating with submerged submarines. The system uses radio waves with a frequency of 76 inverse seconds. So they said that's a frequency. What is the wavelength of this radiation in meters? So are we using different formula or same formula?
Same.
It's the same formula. They've given me frequency. They're asking me for wavelength. So what goes in the numerator?
2.998 times 10 to the 8th meters per second.
Because it's a constant and it will never change. And my denominator this time?
76 inverse seconds.
Right. So if you were off some decimal places on the last one, you probably will not be on this one because you don't have any scientific notation in your denominator. So 2.998 EE8 divided by 76, and how many sig figs should we have?
2.
Only 2, because the 76 only has 2. So this should be a very large number. Are you getting a very large number?
Yep.
Yep. Yes.
3.9 times 10 to the 6th. If your calculator didn't spit it out in scientific notation, make sure that it was six places that you had to move. That is a really long radio wave. Like that's really, really long, which makes sense because it has to get down to the bottom of the ocean to a submarine. So it should be long, very long. Okay, so the next question says violet light has a wavelength of 410 nanometers. So we've got a wavelength, and it asks first, what is its frequency? And then how much energy is 1 photon of light? And what is the energy of 1 mole of photons? Okay, so we actually have 1, 2, 3 questions in one. So if I want frequency and I was given wavelength, which equation am I going to use?
The second one.
The
V.
second one.
Over. Yeah.
Okay, so I need to use this guy. C is still on top. 2.998 times 10 to the 8th meters per second. And now it wants wavelength. I have to enter the wavelength in meters. I was given nanometers. I'm going to do the same trick I did with the megahertz. So I'm going to write 410 times 10 to the, what exponent should I use for nano?
-9.
9.
-9. All right, it's -9 because nano is 9 small. So it's times 10 to the -9. And that way I don't have to worry about anything. I don't need to move the decimal that's understood to be after that 0. Who cares? I'm just entering the calculator. And then that is going to change that from a nanometer to a meter by writing times 10 to the -9. So 2.998 EE8 divided by 410 EE-9.
You got a really big number.
Yes, you should.
Really.
7.3 times 10 to the 14?
3, 6, 9, 12, 14, yeah.
Yes.
Yep. Yeah, your frequency values for visible light are going to be in this range of times 10 to the 14. That's gonna be how you know that you're getting the answer right. Okay, so that's our question for number 1. That's its frequency. And then it wants to know what is the energy. So now I need to look at my two equations that have energy. Which one of those equations do I want if I just calculated its frequency?
The E equals HV.
Yep. I want to use that one because I just got the frequency. And if I can avoid denominators, I would prefer to avoid denominators. I can't always, but if I can, why not? So H is another constant, 6.626 times 10 to the negative 34 joule seconds. All right, those are multiplied. And I'm going to multiply that by my frequency of 7.3 times 10 to the 14th inverse seconds. So you should be able to just kind of eyeball and see that seconds and inverse seconds are going to cancel out. Now, look at your two exponents here. I've got 10 to the negative 34 and I've got 10 to the 14. Those two should cancel out and give me 10 to the what, roughly?
Negative 20.
All right. 14 and negative 34 should give me a negative 20. So that is a way to mentally check to make sure that when you enter this in the calculator, you get something that is correct because the answer should be around 10 to the negative 20. So I've got, again, two numbers that I'm going to enter in scientific notation in my calculator. 6.626 EE negative 34 times 7.3 EE 14. And how many sig figs should I have?
2.
2. And so to 2 sig figs, what are you getting?
4.5.
8.
I mean,
4.8
4.7.
to the negative 19th.
10 to the negative 19.
I got
All right.
4.6. This must be something wrong with the calculator.
And then that's just going to be joules because my seconds canceled out. Okay. The wavelengths of light that are visible to our eyeballs are all in the 10 to the negative 19 joule range, all of them. So I know I specifically asked you for some calculations in the lab to do this energy calculation, and your answers should all be in the 10 to the negative 19 range. That's how you'll know you're doing it right. So that's number 2. Then there's this annoying question number 3. It says, so what's the energy of 1 mole of violet photons? Well, mole implies what number might I need to use?
Avogadro's number.
Avogadro's number, right? Because 1 mole of anything is Avogadro's number of that thing. So 1 mole of photons is Avogadro's number of photons. So to answer that third question, I literally take my energy and multiply it by Avogadro's number. That's it. So my energy was 4.8 times 10 to the negative 19 joules. And I'm going to multiply that by 6.022. Did we use 6.022 in here?
Yes.
Okay. Times 10 to the 23rd. And you're going to do that to 2 sig figs. So 4.8 EE negative 19 times 6.022 EE 23. What do we get?
I got, this is a large number, but it doesn't have an exponent.
That's an adorable child. It should be a large
Thank
number. 2.9 times 10 to the 5th? Does that seem right?
I got.
I got.
Oh yeah.
Yes, that's what I got.
Okay. And that is the same as 290 kilojoules, right? Okay. So there is a whole lot there in question number 4. You're going to want to put a star by question number 4 when you're dealing with the lab and the homework later on, because it's going to be a helpful question to look at. Okay, so we'll look at question 5. We'll save questions 6 and 7 for next week, because they deal with that other equation. So it says the energy of a mole of photons of red light from a laser is 175 kilojoules per mole. Calculate the energy of 1 photon of red light. So that is question number 1. What is the wavelength of red light? That is question number 2, both in meters and in nanometers. And then compare the energy of photon of violet light with those of red light. That was in the previous problem. Okay, so I'm basically doing the opposite of the problem I just did. I started with 175 kilojoules per mole, and I want to know energy of a single one. So I'm already in the per mole. So how do I get a single one? Last time I multiplied by Avogadro's number, so what am I going to have to do this time?
Divide.
Divide. All right. So I'm simply dividing those two numbers. How many sig figs?
3.
3. Okay, so try that in your calculator for 3 sig figs. And what are we getting for 3 sig figs?
2.91 times 10 to the negative 22nd kilojoules.
Yep. And that's kilojoules. If I wanted it in just joules, it would be what? 2.91 times 10 to the
Negative 19th.
negative 19. Because the difference between kilojoules and joules is just 3. So I just take 3 off. Okay. So the other way to remember that it should be times 10 to the negative 19 joules is because all visible light has energy in the times 10 to the negative 19 joule range. All of it. Okay, so that's answer number 1. And then it says number 2, what is the wavelength of light? So I want wavelength and I have energy. So which of these equations am I going to use if I want wavelength and I have energy?
E equals h nu.
Yeah, there's an easier one to use. There's the direct equation that I've rewritten. I'm going to use this guy. I want wavelength. I have energy. These two are constants. That's going to make my life easier. Okay, so I'm going to use wavelength equals h times c over e. All right, so h is a constant. That's Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times the speed of light, 2.998 times 10 to the 8th meters per second. So that'll cancel out those 2 seconds there. My energy, I just calculated, as 2.91 times 10 to the negative 19 joules. So I'm actually going to cancel out the seconds, cancel out there. The joules cancel out there, and it's going to leave me an answer in meters, which should make sense for wavelength. So literally the only thing tricky here is you've got 3 different numbers that are all in scientific notation. And if your calculating device does not have an easy way to do scientific notation, this is going to be why I'm going to send you a virtual TI calculator later. So it would be 6.626 EE negative 34 times 2.998 EE8 divided by 2.91 EE negative 19. 3 sig figs, and you should get a small number because you've got a negative 34 and a positive 8 on top, which is roughly a negative 26. But a negative 26 and this negative 19 down here is not going to chop off everything. So you should still have a negative exponent. And the answer your calculator gives you should be that. Is that what you got?
I don't see where that formula is.
Oh, I hand wrote it at the top.
Oh, okay, thank you.
Mm-hmm. So
Miss
that's,
Baskin,
yes.
I got 6.84 to the negative 7 times 10 to the negative 7.
Okay. Let me re-enter it. Now my calculator gave me 6.82637338 blah 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 blah. You probably just randomly entered one number incorrect. That's fine. So if I wanted to make this into nanometers, that's in meters. Nano means how many?
9.
9. So I'm going to move this 9 spaces. It's 10 to the negative 7. I'm moving it 9 places. So 10 to the negative 7 and 10 to the 9 is going to give me what? 10 to the how many?
10 to the second.
10 to the second. So my answer here is actually going to be 6.83 times 10 to the second nanometers, otherwise known as 683 nanometers. That would be how that works. So comparing the energy of the violet light up here and the red light here, which one had more energy? Which of those numbers is a bigger number? The 2.91 times 10 to the negative 19 or the 4.8 times 10 to the negative 19?
Can you confirm Jameer to come back into the thing?
I did.
4.8 times 10 to the negative 19.
The 4.8 times 10 to the negative 19, the violet light is a higher energy light. Is it tons of energy?
No.
No, it is not very much, but it is the two ends of the visible light spectrum. They are different enough. So yes, we just confirmed that the violet light is about almost twice as energetic as the red light. Not a little under twice as much. So there we go. Okay, so that's all I wanted to get through today. And we will touch on 6 and 7 next week. And that's it. So let me switch back over to this guy. Okay, so Thursday, we were supposed to do our lab on Thursday. But it means we have DC Emancipation Day, which is a great thing, but it means we don't have class. So yay, everybody. None of your teachers should be having class that day. None of your arts teachers, nobody should be having arts or any sort of class. So if one of your teachers does say that you're still going to have class, remind them that DC government said you are closed. And if you don't feel comfortable doing that, tell me and I can send them an email in a way that you do not have to put yourself out there with your teacher. So if you do have a teacher who's telling you to have class on Thursday, let me know. Okay. So it was going to be a really short class for us because I was literally just going to go over how to do the pre-lab questions. And I was going to burn stuff for you. And that was going to be it. Instead, this afternoon, I will record me burning stuff and going over the pre-lab question. And the link for the actual Google form to do the lab is on the weekly plan for the week. And I'm just going to put a video, a link to a YouTube video now at the top of that Google form. And I will also put it in the plan and I'll email it out and all of those things. But the lab was going to be due Thursday because we were going to do almost all of it together in class. So now, like everything else, it'll be due on Monday. So the lab was the one thing we were, the one assignment you had due for me this week. But since we don't have class on Thursday, it just doesn't feel right to say it's now due Friday. So I will now say it's due Monday. You'll be able to do it anytime after I do the recording of me burning stuff, and I will let you know when I do that recording. So if you have free time today or tomorrow, or you want to do it Thursday or Friday, whenever, it'll just be due. It'll just be due on Monday night. So it is much, much shorter than the calorimetry lab that you did. So that will be easy. So reminders about the rest of this week. I do have office hours tomorrow from 1 to 2 for you guys specifically. I'm canceling out Thursday's office hours because if they're telling me to take a day, damn it, I'm going to take a day. And then I also have office hours on Friday. So if you want to do part of the lab with me on either of those days, that's fine. Or you want to help going over those calculations, that's fine. A new Edpuzzle video did open this morning. That's also due on Monday. So you've got the virtual lab and the Edpuzzle. Those are your only assignments that are open right now. I am telling you in advance that the 5.2 and 5.3 homework will be due next Thursday. So you can get started on that whenever you have time. And there are calculations on that. So you should start looking over that. And if you need or want to do some of those calculations on that homework with me, office hours are a good time to do that. You can also send me remind chats doing stuff. We will start going over 5.4 next week, but I believe let's see here, the 5.2 and 5.3 homework would be the very last possible thing I would include for as a way to boost grades for term 3. So that will be the last thing that will be term 3. All of the 5.4 stuff will end up being term 4, assuming we still have term 4, because, you know, we're supposed to go back to school in less than 2 weeks and that ain't happening, but they haven't said anything. So, you know, fun times. All right, so questions now. Whew.
Wait, didn't the mayor say that we're not going back on the 27th?
Yeah, I mean, in an offhand sort of flippant comment, yes, she did. But did they ever provide any more information? No, she did not. So we know that's not happening, but we don't know. We don't know what's different.
Mm-hmm.
Yeah. But yeah, at the end of like a press conference, I don't even think it was last week. I think it was the Friday before. She was like, "We're not going back on the 27th." In response to somebody's question, and everybody was like, "Oh, okay. So what are we doing?" And she was like, "We'll figure it out. We'll let you know." And it's like, okay. They haven't let us know yet. Other questions?
So should we do were we supposed to already have done 5.2 and 5.3?
The reading guides, yes. But I mean, again, reading guides now are just for you. Those are not things you have to show me anymore, because that would be way too much scanning and my email would blow up with scans of stuff. Like, it's fine. They were always supposed to be for you. And I just gave them a minor grade to force you to do them. But that's, since we're only meeting once or twice a week now, like, you're going to be a little bit more dependent on figuring things out from those reading guides.
I have a question. Does section 5 end with 5.4? Because like,
Yes, it
I
does.
okay, because I thought it was short and I couldn't like
Yep.
find any more notes after it, so I was
Nope,
really
it does.
confused.
Yes, Ashton, class is over. You can leave if you don't have any questions.
So what is gonna happen once we reach our mark there and we don't have any more work?
We do have more work. I just haven't given it to you. So one of the things I'll have to do is, as we move into section 6, I will have to see who has the ability to print and who doesn't. And if we basically have, even a quarter of the class who can't print stuff, then I'm going to have to basically shift directions into a moderately different way. So I will still give you the reading guides and the sections so that you have those, but then we'll really move to no paperwork, where I will probably transition the class to Google Classroom and you'll have docs to submit.
Okay.
Yeah. So. Other questions? Okay.